Hello students. Limits and derivatives is the base of calculus. Today we are going to discuss limits from class 11. To understand the concepts and examples, watch the video till the end. Basically, calculus is the branch of mathematics which deals with the study of change in the value of a function as the points in the domain change. Limit describes how a function behaves near a point instead of that particular point. The limits are defined as the value that the function approaches as it goes near a particular value. We say that limit x tends to a minus f of x is the expected value of the function f at x equal to a given the values of f near x to the left of a. That means as your x values approach a from the left hand side, whatever is the expected value of f, that is called the left hand limit of f. Similarly, we say that limit x tends to a plus fx is the expected value of f at x equal to a given the values of f near x to the right of a. Means as your x approaches a from the right hand side, whatever is the expected value of f, that is called the right hand limit. And very important, remember, if the right and left hand limits coincide, means if they are same, then we call that common value as the limit of the function f at x equal to a, and it is denoted by limit x tends to a fx. Let us take an example to understand the limits. Consider the function fx equal to x plus 10. We want to find the limit of the function at x equal to 5. Let us compute the value of the function fx for every x which is close to 5. That means, again I am repeating that in limits we don't find the value of the function at that particular point, but we find the value of the function when the x value approaches that particular value. So we take the values which are near to 5 like 4.9, 4.95, 4.99, 4.995, 5.001, 5.01 and 5.1. And when we put this x value in our function fx is equal to x plus 10, we get the following values of fx. Now you can see very well that when the value of x approaches 5 from the left hand side means 4.9599, 4.995, that is from the left hand side. At that time, the value of fx also approaches 15. That means 14.99, 14.995. So it is approaching 15. Similarly, when your x value approaches 5 from the right hand side, 5.1, 5.01, 5.001, fx value also approaches 15, 15.1, 15.01, 15.001. So precisely it goes near 15. Hence, the left hand and right hand limits are same and that value is called the limit of the function. Hence, the limit of the function is 15 and the value of the function at x equal to 5 is also 15. Remember, I have taken this explicitly because in this case, the limit of the function and the value of the function at that particular point is same. It does not happen always. Anyway, for this example, limit x tends to 5 fx is equal to f of 5, means the value of the function at x equal to 5. Another example to understand limits, find limit x tends to 0 fx where fx is defined as x minus 2 if x is less than 0, fx is exactly equal to 0 if x equal to 0 and fx is x plus 2 if x is greater than 0. Now for this function, if you try to evaluate the values of fx for x which are near to 0, you want to find x tends to 0. That means from the left hand side and from the right hand side. So from the left hand side means minus 0.01, minus 0.001. From the right hand side means 0.01, 0.001. Now when you take x is equal to minus 0.01, you will use the function fx is equal to x minus 2. And that will give you minus 2.01. Similarly, when you take x equal to minus 0.001, fx is x minus 2 because x is less than 0 and so fx is minus 2.001. Now remember, if x is 0.001, at that time since x is greater than 0, what is the definition of fx in our example? Fx is equal to x plus 2. So when x is 0.001 or say x is 0.01, in that case you will find fx using fx is equal to x plus 2. The values in the table are given. We have obtained these values. So if you see from the left hand side, the value of fx minus 2.01 minus 2.001, so it approaches minus 2. But if you see the value of fx from the right hand side, it is 2.01, 2.001, means it approaches the value 2. So the left hand limit in this case is minus 2 and the right hand limit in this case is 2. And since they are not equal, since they don't coincide, we say that the limit of the function at x equal to 0 does not exist. Now in this example, what has happened is the value of the function f at 0 exists. It is already given in the definition of function that fx is equal to 0 if x equal to 0, means fx is equal to 0, value of function f exists at x equal to 0, but limit of the function at x equal to 0 is not defined in this case. Third different case. Find limit x tends to 1 fx where fx is equal to x plus 2 if x is not equal to 1 and is equal to 0 if x equal to 1. And you have to find limit x tends to 1 fx. X tends to 1 means from the left hand side and from the right hand side I take the values of x which are nearby 1. So 0.9, 0.99, 0.999, 1.001, 1.01 and 1.1. Again, x is not, whenever in all these cases x is not exactly equal to 1. So what is the definition of fx given in our example? Fx is equal to x plus 2. So put these values of x in fx equal to x plus 2. You will get the value of corresponding fx. Now if you observe carefully, as x tends to 1 from the left hand side, means 0.9, 0.99, 0.999. What is the corresponding value of fx? 2.9, 2.99, 2.999. Means it is approaching 3. Similarly, as x tends to 1 from the right hand side, 1.1, 1.01, 1.001 from the right hand side, at that time also the value of fx is approaching 3. So in this case, both left hand and right hand limit are same. So the limit of the function exists and its value, that means the limit of function as x tends to 1 fx is 3. So what has happened in this case? The limit of the function exists at a given point, but it is not equal to the value of the function at that point. Why? If you see our function, how it is defined in the example, fx is equal to 0 if x equal to 1. So at x equal to 1, the value of the function is 0, but the limit of the function is 3. So it can happen that at a given point, the value of the function and its limit may be different, even if both of them are defined. So we have taken these three cases: when limit exists, when limit does not exist, and sometimes it happens that the limit exists but it is not same as the value of the function at that particular point. Some important theorems on limits. Theorem 1. Let f and g be two functions such that both limit x tends to a fx and limit x tends to a gx exist, and say c is any real number. Then limit x tends to a c into fx is equal to c into limit fx x tends to a. Second case, limit of the addition or subtraction of two functions, means limit x tends to a fx plus or minus gx is same as limit x tends to a fx plus or minus limit x tends to a gx. Same way multiplication, limit x tends to a fx into gx is limit x tends to a fx into limit x tends to a gx. And same way for division, limit x tends to a fx upon gx is equal to limit x tends to a fx upon limit x tends to a gx, provided limit x tends to a, gx is not equal to 0. Theorem 2. This is an important theorem which is used in many examples. For any positive integer n, limit x tends to a, x raised to n minus a raised to n upon x minus a is equal to n into a raised to n minus 1. We will prove this theorem. So now what we do is divide x raised to n minus a raised to n by x minus a. So what will you get? X raised to n minus a raised to n is equal to x minus a into x raised to n minus 1 plus x raised to n minus 2 into a plus x raised to n minus 3 into a square up till a raised to n minus 1. apply limit on both the sides. Just now we have seen that addition of two functions, limit for that is the limit of the first function plus the limit of the second function. So limit x tends to a, x raised to n minus 1 means instead of x you put a, so it is a raised to n minus 1. Second term, limit x tends to a, x raised to n minus 2 into a. So take a outside, limit x tends to a, x raised to n minus 2 is a raised to n minus 2. So second term is a into a raised to n minus 2. Similarly, up to the last term, a raised to n minus 1. So first term is a raised to n minus 1. Second term will also become a raised to n minus 1. Similarly, all the terms will be a raised to n minus 1. There are n such terms. So this is equal to n into a raised to n minus 1. So we have proved limit x tends to a, x raised to n minus a raised to n upon x minus a is equal to n into a raised to n minus 1. Now remember, we are taking over here positive integer n, but if n is any rational number, this theorem will hold true. So for any rational number n and for a positive, this theorem will be true. Theorem 3. Let f and g be two real valued functions with the same domain such that fx is less than or equal to gx for all x. For some a, if both limit x tends to a fx and limit x tends to a gx exist, then limit x tends to a fx will be less than or equal to limit x tends to a gx. Means if fx is less than or equal to gx, the limit will also behave in the same way. From this we get the next theorem, which is called the sandwich theorem. It says that let f and g and h be real functions such that fx less than or equal to gx less than or equal to hx, means gx lies between fx and hx for all x in the common domain of definition. For some real number a, if limit x tends to a fx is equal to say L, and that is same as limit x tends to a hx, that means if the limit of the function fx and hx at x tends to a is same, then that will again be the limit of the function which is in between, means limit x tends to a gx will also be equal to L. So if the limit of fx and hx is L, limit of gx will also be equal to L in this case. Theorem 5. This gives the trigonometric functions limits. First one, limit x tends to 0, sin x upon x is always 1. Limit x tends to 0, 1 minus cos x upon x is equal to 1. And limit x tends to 0, tan x upon x is also equal to 1. Now remember, first and 2 are the limits for sine and cos function. Now the third case means the limit for the tan function can be proved using 1 and 2. Why? Because limit x tends to 0, tan x upon x is same as limit x tends to 0, sin x upon cos x. Now sin x upon x, take that different. So it is limit x tends to 0, sin x upon x into limit x tends to 0, 1 upon cos x. But we know that limit x tends to 0, sin x upon x is 1. And for the second term, when you put x as 0, you know cos 0 is 1. So 1 upon 1 is 1. So basically this limit is 1 into 1, which is again equal to 1. So remember these three limits. Now we take different types of examples. In each of the examples we need to evaluate the limits for the given functions. First one, find limit x tends to 1, x raised to 15 minus 1 upon x raised to 10 minus 1. So we are going to use that important result, limit x tends to a, x raised to n minus a raised to n upon x minus a is n into a raised to n minus 1. So now what we do is x raised to 15 minus 1. That means you can write that as x raised to 15 minus 1 raised to 15. So your n is 15 in this case. If I can divide by x minus a, what is your a? A is 1. So I will divide by x minus 1. If I divide by x minus 1, I have to multiply by x minus 1. So I divide and multiply by x minus 1. So now you split the two limits. Limit x tends to 1, x raised to 15 minus 1 upon x minus 1 divided by limit x tends to 1, x raised to 10 minus 1 upon x minus 1. So for both of them, use the above formula. So in the first case, your n is 15. So it is 15 into a. A is 1. Anything raised to 1 is 1. So it is 15 into 1. your denominator will be x raised to 10 minus 1 means here your value of n is 10. So it is 10 into 1 raised to 9, but 1 raised to anything is 1. So it is 15 upon 10 or 3 by 2. Second one, limit x tends to 0, root of 1 plus x minus 1 upon x. Now we want to use our result on the limits. So take 1 plus x as some y. So y minus 1 will be equal to x because we have taken 1 plus x as y minus 1 is x. So now in the given question, as x tends to 0, if x tends to 0, what will y tend to? Y tend to 1. Why? Because we have taken y minus 1 is equal to x. So as x tends to 0, y will tend to 1. So remember, if you make these type of assumptions, then you need to simultaneously change the point at which you are taking the limit. So when x tends to 0, y tends to 1. So our example will become limit y tends to 1. What is the numerator? Root of 1 plus x means root of y, or y raised to half, minus 1. 1 I can write as 1 raised to half. And what is x? X is y minus 1. So we have converted in the form of our result, limit x tends to a, x raised to n minus a raised to n upon x minus a. What is our n over here? N is half. So this is equal to half into a. A is 1. So 1 raised to anything is 1. So this is equal to half. Fifth example. Here you have to find the limit for a polynomial function. Find limit x tends to 3, x raised to 4 minus 81 upon 2x square minus 5x minus 3. Now see, remember this point, there is a rule. This rule, remember always, a general rule is that suppose if you need to find limit x tends to a fx upon gx, then what we do is we first put the value of x as a in both the functions. And if we get the limit is okay. But if we get it in the form of 0 by 0, then in that case we need to factorize the function further. We will not accept it as it is. So for each of these type of examples, what we will do is we will see that if we get the limit as 0 by 0 form, then we will further factorize it. So in this case, suppose if I put x equal to 3 in the numerator, then I will get 0, and similarly if I put x equal to 3 in the denominator, then also I will get 0. So it is of the form 0 by 0. So we need to further factorize the function. Now factorizing it, we will use difference of two squares. So x raised to 4 minus 81 is x raised to 4 minus 9 square. So it is x square plus 9, x square minus 9. But again x square minus 9 is x minus 3, x plus 3. Same way, denominator, you split the middle term. So 2x square minus 6x plus x minus 3. So you will get the factors 2x plus 1, x minus 3. X minus 3 get cancelled out. So now what we get is limit x tends to 3, x square plus 9, x plus 3 upon 2x plus 1. So now you put the value of x as 3 in this numerator and denominator. You will be getting it as 108 by 7. Example 6. Evaluate limit z tends to 1, z raised to 1 by 3 minus 1 upon z raised to 1 by 6 minus 1. Now here also we use our result, and in that result, if you remember, I told you that it is not necessary that n is positive only. N can be any rational number, correct? So in this case, z raised to 1 by 3 minus 1, you divide and multiply the whole function by z minus 1. So numerator will become z raised to 1 by 3 minus 1 upon z minus 1 upon z raised to 1 by 6 minus 1 upon z minus 1. So now use our result. In the numerator, your value of n is 1 by 3. 1 by 3 into 1 raised to 1 by 3 minus 1. But 1 raised to anything is 1. So numerator is 1 by 3. Denominator is 1 by 6. So the answer for this, the limit is 2. Example 7. Evaluate limit x tends to 0 sin ax upon sin bx, where a and b are not equal to 0. Here we use our limit of trigonometric function for sine. That means we have the formula limit x tends to 0, sin x by x is 1. What we do is we multiply and divide by ax and bx. So numerator sin ax into bx, denominator sin bx into ax into bx. But we know limit x tends to 0 sin ax upon ax. We are using the above result, that will be 1. Similarly, limit x tends to 0, sin bx upon bx will also be 1. So it is 1 into ax upon 1 into bx. Xx gets cancelled out. So this is equal to a upon b. Hence the limit for this function is a upon b. Evaluate limit x tends to 0, cos 2x minus 1 upon cos x minus 1. Now first of all it is in the 0 by 0 form. Remember, in all the examples first you check it and generally it will be in the 0 by 0 form, so you will need to further simplify it. Because if I put x as 0, cos 0 is 1, so 1 minus 1 0, even denominator 1 minus 1 0, 0 by 0 form. So we need to further factorize it. Now since the denominator is in the form of cos x, let us convert cos 2x in the form of cos x. So we know this trigonometric formula, cos 2x is 2 cos square x minus 1. So limit x tends to 0, 2 cos square x minus 1, the function, upon cos x minus 1. Take out 2 common. So you will get cos square x minus 1, you simplify by a square minus b square rule. So numerator will be 2 into cos x minus 1, cos x plus 1 upon cos x minus 1. Cos x minus 1 will get cancelled out. So ultimately you are having limit x tends to 0, 2 into cos x plus 1. Now you put x as 0, you know cos 0 is 1. So it is 2 into 1 plus 1, which is equal to 4. So the limit of this function is 4. Find limit x tends to pi by 2 tan 2x upon x minus pi by 2. Now again first of all check over here. It is in the 0 by 0 form, because if you put x equal to pi by 2, tan pi is 0 and the denominator is also 0. So now we need to further simplify it. Now looking at this, since we are having x minus pi by 2 in the denominator, take x minus pi by 2 as some z. So now as in the original function x tends to pi by 2, what will z tend to? Z will tend to 0. Also x minus pi by 2 we have taken equal to z. So this gives 2x equal to pi plus 2z. So now the original, it will become limit z tends to 0. Instead of x tends to pi by 2, now we have converted the function from x to z. So it will be limit z tends to 0, tan of 2x. 2x means pi plus 2z upon z. But what is tan of pi plus 2z? You know tan of pi plus theta is tan theta. So it is tan z tends to 0, limit z tends to 0, tan of 2z upon z. Multiply and divide by 2. So you will get 2 into tan, limit of tan 2z upon 2z. But we know that limit x tends to 0, tan x upon x is equal to 1. So it is 2 into 1, which is equal to 2. So the limit for this function is 2. Limit x tends to 0, cosec x minus cot x. Now first simplify this. Cosec x is 1 upon sin x and cot x is cos x upon sin x. So this is limit x tends to 0, 1 minus cos x upon sin x. Now multiply and divide by x. So what will you get? Limit x tends to 0, 1 minus cos x upon x upon limit x tends to 0, sin x by x. You know that limit x tends to 0, sin x by x is 1 and limit x tends to 0, 1 minus cos x by x is 0. So this is 0 upon 1 or 0. So 0 upon 1 is 0. So the limit for this function is 0. Example 11. Evaluate limit x tends to 0 fx, where fx is defined as mod x upon x if x is not equal to 0 and 0 if x is equal to 0. Now the limit of a function exists if and only if your left hand and right hand limit exist and they are same. Correct? So now what we try to do is we try to find the left hand and right hand limits for this function. Also let us recall that what is mod x. The function mod x is defined as minus x is if x is less than 0. Means suppose if you are having mod of minus 5, then that is equal to 5. Because over here your x is less than 0, your function value is minus of minus 5, which is 5. In short, mod x function is defined in this manner. Fx is equal to minus x is if x is less than 0 and is equal to x if x is greater than or equal to 0. So now we try to evaluate the left hand and right hand limits for this function. Limit x tends to 0 from the left side. That means limit x tends to 0 minus mod x upon x is equal to Remember, since over here x tends to 0 from the negative side, so your value of x is less than 0. So from the definition of function of modulus, what is it? It is minus x. So it is minus x upon x, which is equal to minus 1. Limit x tends to 0 plus, that means from the positive side when your x tends to 0, it is mod x upon x, but in this case your x is greater than or equal to 0. So fx is x by the definition of mod function. So this limit is equal to x upon x, which is gives you 1. So in this case we have found that limit x tends to 0 minus and limit x tends to 0 plus, both left hand and right hand limits are not the same. So the limit of this function at x tends to 0 does not exist. So remember, this is the case in which the limit x tends to 0 fx does not exist, even though the value of the function fx exists at x equal to 0. Another different example. Suppose if fx is defined as a plus bx if x is less than 1, fx is 4 if x is equal to 1, and fx is b minus ax if x is greater than 1. Limit x tends to 1 fx is same as f of 1. If this is true, then find the possible values of a and b. Correct? Now over here, when will limit x tends to 1 fx exist? When both left and right limits will be the same. So first thing is we find the limit from the function from left and right side. So limit x tends to 1 minus fx equal to limit x tends to 1 a plus bx. Why? Because when x tends to 1 from the left hand side, how is the function f defined? When x less than 1, the function f is defined as a plus bx. So limit x tends to 1 minus fx is limit x tends to 1 a plus bx. Here put x as 1, you will get a plus b. Now find the right hand limit. Limit x tends to 1 plus fx. That means if your x is tending to 1 from the right hand side, in this case your x is greater than 1. So how is the function defined in this case? B minus ax. So for this case it is limit x tends to 1 b minus ax. Put x equal to 1, you will get b minus a. Now see, it is given over here that this limit exists, means this left hand and right hand limit should be same, means your a plus b and b minus a should be equal. So first thing is a plus b should be equal to b minus a, and also when the limit exists it is same as f of 1. That is also what they have given. But what is f of 1? The value of the function at x equal to 1 is 4 by the definition given in the function. So a plus b is same as b minus a, and both of them are equal to 4 because this is given to us in the question. So first of all, what we get is 2a is 0. Since a plus b is equal to b minus a, 2a is 0. So a is 0. In a plus b equal to 4 or say b minus a equal to 4, in any of this case put a equal to 0, you will get the value of b as 4. So the possible values of a and b are 0 and 4 respectively. If fx is defined as mod x plus 1 when x is less than 0, fx is 0 if x is equal to 0, and fx is defined as mod x minus 1 when x is greater than 0. For what value or values of a does limit x tends to a fx exist? Now since you want for which values limit x tends to a fx exist, there will be three possible cases for your a. Your a can either be exactly equal to 0 or less than 0 or greater than 0. So we will take one by one each case. Suppose if a is exactly equal to 0, we first of all trying to find the left hand and right hand limits. Left hand limit x tends to 0 minus. In this case limit x tends to 0 minus means x is approaching 0 from the left hand side. So in this case the values of x will be less than 0. How is function defined when x is less than 0? Mod x plus 1. So this is equal to limit x tends to 0 mod x plus 1. But when x is less than 0, how is mod x defined? We have just seen in a previous example, mod x is minus x. So this is limit x tends to 0 minus x plus 1. Put x as 0, you will get this equal to 1. Now the right hand limit. Limit x tends to 0 from the right hand side. Means right hand side means all the values of x will be greater than 0. In this case, how the function is defined? Mod x minus 1. So the right hand limit will be limit x tends to 0. Mod x, what will be value of mod x when x is greater than 0? Mod x is same as x. So this will be limit x tends to 0, x minus 1. Put x as 0, you will be getting this as minus 1. So what has happened is limit x tends to 0 minus and limit x tends to 0 plus. Both are not the same. So the limit of the function at as x tends to 0 does not exist. So when a is equal to 0, your limit does not exist. Second case, if a is less than 0. In this case, we again find the left hand and right hand limits. Remember, a is less than 0. Limit x tends to a minus means we are approaching a from the left hand side. Now remember, in this case, which definition of function you will use? Since your a is less than 0, you will use the definition of function fx is equal to mod x plus 1. Because when a is less than 0, this is what we need to use. So don't get confused. In this case, we use which definition of function? Fx is mod x plus 1. Now we find the left and right hand limits. Limit x tends to a minus mod x plus 1 is equal to limit x tends to a. But when a is less than 0, what is mod x? Mod x is minus x. So it is limit x tends to a minus x plus 1. Put x as a, it is minus a plus 1. Similarly, when x is tending to a from the right hand side, mod x plus 1. So this is again limit x tends to a minus x plus 1 minus a plus 1. So both left hand and right hand limits are same, and which is equal to minus a plus 1. So this itself is the limit x tends to a fx. Left and right hand limits should be equal, so that will give you the value of the that will give you the limit of the function. Third case, when a is greater than 0. Again, when a is greater than 0, which definition of function you will use? Mod x minus 1. Correct? So if a is greater than 0, the left hand limit is limit x tends to a minus mod x minus 1, which is limit x tends to a. When a is greater than 0, mod x is same as x. So this is limit x tends to a, x minus 1. Put x as a, so it is a minus 1. Similarly, limit x tends to a plus mod x minus 1 is limit x tends to a, x minus 1. Put x as a, it is a minus 1. Your left hand and right hand limits are same, and that is equal to a minus 1. So in the third case, if a is greater than 0, the limit of the function is a minus 1. In this video, we have seen the concepts and all the important examples based on limits. Subscribe to the channel for the next video, in which we are going to study derivatives, which is the base of calculus and a very important topic.